What if I told you the most advanced robots in the world still struggle to pick up a sock? We see viral videos of humanoid robots doing backflips, walking smoothly, even cooking. It looks like science fiction becoming reality. But how do these machines actually learn to move? How do they see? How do they make decisions? And why is it still so hard for them to function like humans? Today, we're breaking down how AI-powered robots really work. Not the hype, not the marketing, the real mechanics behind the machine. Let's start with movement. For a robot to move like a human, it needs three core systems. First, sensors. Second, actuators. Third, a control system, the brain. Sensors are how robots perceive the world. Cameras act as eyes. LiDAR scans the environment using lasers. Microphones detect sound. Touch sensors measure pressure and contact. But raw sensor data is useless without interpretation. That's where AI comes in. Modern robots use neural networks, similar to the systems behind ChatGPT, to process visual and spatial data. When a robot sees a chair, it doesn't see a chair like we do. It detects edges, depth, shape patterns, and probability. Its AI model calculates there is a 94% chance this object is a chair. It is approximately 1.2 meters away. It can support weight. Everything is math. Everything is prediction. Now let's talk about movement. Actuators are the robot's muscles. These can be electric motors, hydraulic systems, or advanced servo mechanisms. When you take a step, your brain automatically adjusts for balance, terrain, and body weight. For a robot, this must be calculated in real time, hundreds of times per second. If a humanoid robot leans forward just slightly too much, it falls. So engineers use something called dynamic balance control. The robot constantly calculates its center of mass and adjusts motor torque accordingly. This is why walking robots consume so much power. They are constantly correcting themselves. Now here's where it gets interesting. How do robots actually learn these movements? One method is called reinforcement learning. Instead of programming every possible movement manually, engineers let the AI learn through trial and error, often in simulation. Imagine a virtual robot in a digital world. It tries to walk, it falls. The AI updates its model, it tries again. Millions of attempts later, it learns balance. But here's the key. Most learning happens in simulation first, because letting real robots fall thousands of times would destroy hardware. Once the AI masters movement digitally, that knowledge is transferred to the physical robot. But even then, the real world is unpredictable. Floors are uneven, objects move, lighting changes, which is why robots that look smooth in controlled demos can struggle in normal environments. Now let's talk about decision making. Robots don't think the way humans do. They operate through layered systems. At the lowest level, reflex control. At the middle level, motion planning. At the highest level, task planning. For example, if you tell a robot, go to the kitchen and grab a bottle, the task planner breaks this down into steps. Navigate to kitchen, identify bottle, plan grip trajectory, adjust force, lift object. Each step requires separate models working together, and every step has uncertainty. That's why robots can assemble cars in factories with incredible precision, but struggle to fold laundry at home. Factory environments are predictable, homes are chaotic, and chaos is the hardest problem in robotics. So where are we heading? The future of robotics is about combining large AI models with physical intelligence. Right now, AI is extremely good at language and digital reasoning, but physical reasoning, understanding gravity, friction, texture, is still developing. The next breakthrough won't just be smarter software. It will be AI that understands physics intuitively. When robots can reliably manipulate objects in unpredictable environments, that's when you'll see them in homes, hospitals, construction sites, everywhere. So the next time you see a humanoid robot walking smoothly on stage, remember, behind that smooth movement are thousands of calculations per second, years of engineering, and millions of simulated failures. Robots aren't magic. They're probability machines. And they're getting better, one calculation at a time. This is how it really works.